Hello students, let us have a look at our 8th chapter, that is dual nature of matter and radiation. After studying this chapter, you will be able to understand the concept of electron emission, explain photoelectric effect, describe the experimental study of photoelectric effect, define photoelectric effect and wave theory of light, discuss on Einstein's photoelectric equation, energy quantum of radiation, understand the particle nature of light, the photon, define wave nature of matter, explain Davisson and Germer experiment. Let us start off with how the cathode rays came into being and how this led to the discovery of the electron. By the mid-1800s, scientists were experimenting with high voltage induction transformers in conjunction with evacuated glass tubes, Crookes tubes. A new phenomenon was discovered which came to be called cathode rays. Various experiments were performed in an effort to identify the nature of these mysterious rays. The first of these experiments, which demonstrate cathode rays, are influenced by a magnetic field. Therefore, the rays themselves must carry a charge. This induction coil produces high voltage, 5 kV to 10 kV, pulsed DC current from a low voltage -6V to 12V direct current source. The design is comparable to the ones used in the 1800s. Changing the polarity of the magnet attracts or repels the beam. At sufficiently low pressure of about 0.001 mm of mercury column, a discharge took place between the two electrodes on applying the electric field to the gas in the discharge tube. A fluorescent glow appeared on the glass opposite to cathode. The color of glow of the glass depended on the type of glass. The cause of this fluorescence was attributed to the radiation which appeared to be coming from the cathode. These cathode rays were discovered in 1870 by William Crookes. Later, in 1879, he suggested that these rays consisted of streams of fast-moving negatively charged particles. In 1897, J.J. Thomson, an English physicist, determined the charge to mass ratio over the electrode. He adjusted the electric field so that the electrostatic deflection theta E was the same as the magnetic deflection theta B. He was able to calculate the charge to mass ratio of an electron using the following equation, where E is the applied electric field, theta is the angle of deflection, B is the applied magnetic field, and I is the distance travelled by the cathode rays. Thomson determined that the charge to mass ratio of an electron is negative 1.76 times 10 to the 8 coulomb per gram. For his epoch-making discovery of electron, he was awarded the Nobel Prize in Physics in 1906. Electron emission, photoelectric effect. Now let us take a look at this experiment. Ground the system by touching the metal. Give a PVC pipe a negative charge by rubbing it with a dry cotton cloth. Now transfer the negative charge to the tinsel by touching the charged PVC pipe to the tinsel or any attached metal. Negatively charged tinsel icicles repel each other. Now instead of touching the metal to ground the system, which will cause the tinsel to fall down, we are going to use light. You all must be wondering, how can light discharge the tinsel? This is possible because of something known as the photoelectric effect. In a nutshell, the photoelectric effect is the emission of electrons when a surface is exposed to photons of sufficient energy. Let us try it. You can see that the tinsel has been holding its charge under household lighting. Why don't we try some more energetic photons, the ultraviolet light? Now, a convenient source of ultraviolet light is a portable germicidal lamp. Carefully focus the UV ray at the aluminium pan. As the electrons are emitted from the light, you can see that the tinsel loses its charge. Now exposure to UV radiation is harmful. You have to be cautious while using it. Photoelectric effect. Now let us find out how light of different frequencies behave with metal silver here. We are doing this experiment in vacuum as we are looking for electrons that jump out of the metal. So first we will start with red light, let's say 615 nanometers. We shine this red light on silver and we get no electrons produced. We can do this at low intensity or at high intensity and still we do not get any electrons. Now we change the wavelength of light to 515 nanometers. This is green light. So the frequency is now higher, but we get nothing in terms of electrons coming out of the metal, either at low intensity or at high intensity. So we reduce the wavelength of light and go to the ultraviolet region of the spectrum. Now we find that there is a cutoff at 263 nanometers. If we have a wavelength below that, we get electrons coming out of the metal. Now at low intensity we get few electrons produced and at high intensity we get lots of electrons produced. Thus you see that it takes a certain amount of energy for an electron to escape the metal. Electrons absorb this energy from the light. The photoelectric effect refers to the emission or ejection of electrons from a metal surface in response to incident light. Energy contained in the incident light is absorbed by electrons within the metal, giving the electrons sufficient energy to be knocked out of or emitted from the surface of the metal. In 1905, Einstein proposed that the incident light considered of individual quanta called photons that interacted with the electrons in the metal like discrete particles rather than as continuous waves. For a given frequency or color of the incident radiation, each photon carries the energy E as equal to h nu, where h is a Planck's constant and nu is the frequency. Albert Einstein was honored with the Nobel Prize in Physics in 1921 for successfully explaining the photoelectric effect. Photoelectric cell. Now we shall look at the photoelectric cell. The photoelectric cell, also known as the phototube, is an electron tube in which the electron initiating an electric current originates by photoelectric emission. A phototube consists of a cathode coated with a photosensitive material and an anode. Light falling on the cathode causes the liberation of electrons, which are then attracted to the positively charged anode, which results in the flow of current. Now these phototubes are either evacuated or filled with an inert gas at low pressure to achieve greater sensitivity. If a series of metal plates are arranged in the electron tube, then the photoelectric emission is amplified by secondary electron emission. This type of tube, where there are number of tubes, is called a photomultiplier. A photomultiplier is capable of detecting radiation of extreme low intensity. Hence, it is used as a radiation detector in nuclear research. Photoelectric effect. Now, this setup here on the screen is meant for an experimental study of the photoelectric effect. Now, you all have the basic know-how of the photoelectric effect. So, as you can see, we have an evacuated glass tube which has a photosensitive plate. Let me label it as C. This is known as the emitter. Now there's another metal plate A known as the collector. You can see that the emitter and the collector are attached to a battery which maintains a potential difference between the plates. You can also see a small window that opens up into the glass tube. It is a transparent quartz window that permits UV radiations to pass through it and irradiate the emitter. Now, monochromatic light from a source of sufficiently short wavelength passes through this window and falls on the photosensitive plate C, which is the emitter. Because of photoelectric effect, the electrons are emitted by the plate C and are collected by plate A by the electric field created by the battery. When the collector plate A is positive with respect to the emitter plate C, the electrons are attracted to it. The emission of electrons causes flow of electric current in the circuit. Experimental study of photoelectric effect. The photoelectric effect shows that when light strikes a metal surface, electrons are ejected from that metal surface. Now the first thing that we need to know is that brighter the light, the greater the current. That is, greater number of electrons are ejected from the metal with brighter light. You will notice that it is a linear relation. So no matter how low your intensity is, as long as it is not zero, you will still have some electrons ejected from the metal. The second that we need to know is that these electrons ejected from the metal have a certain amount of energy. We determine that energy by using a voltage source. So we make one of these plates negative and it starts repelling the electrons from it. Now with just the right voltage adjusted, you see that none of the electrons reach the plate. At that point, the current will drop down to zero. Once the current is zero, we can find the energy of these electrons by using the formula voltage equal to the work upon the charge of electrons. Let us now see if there is any relation between the energy of electrons and the light shining on the surface of the plate. Notice the graph carefully. As we increase the frequency of the light by decreasing the wavelength, you will notice that the energy of electrons increases. Similarly, if we lower the frequency of the light, the energy of electrons decreases. Eventually, there is a point where no more electrons are ejected from the metal. At that point, you have been set to cross the threshold frequency for that material. From that point on, no more electrons will be ejected, and each type of metal will have its own threshold frequency. Particle nature of light, the photon. Let us recall the three things related to wave theory. We use a low frequency wave, we do not get any photoelectrons. When we increase the amplitude of the wave, we expect to eventually get the photoelectrons, but we did not. So we switch to a higher frequency wave and finally get the photoelectrons. If we increase the amplitude of the wave, we expect the photoelectrons to come out energetically, but we did not. If we reduce the amplitude of the wave until it is a very small, then it takes very long for an electron to come out. Photoelectric effect did not make any sense until Einstein came along. He thought we cannot solve all problems thinking that light travels in a wave. Einstein went ahead and asked, what if there was no wave at all? What if light does not give out energy continuously as wave, but in lumps as particles do? Einstein called his light particles photons. He proposed E is equal to hf, that each photon carries energy equal to Planck's constant times the light frequency. Suddenly, photoelectric effect makes sense. Let us put this in a figure. Threshold frequency is the frequency when energy of the photon hf is equal to the work function. For this threshold frequency, none of the photons have the energy to overcome the work function. Increasing the intensity of light does not help. It only brings more photons. The only way to knock out electron in one single punch is to increase the frequency of light until the energy of electron is more than the work function. Since it is a simple energy transaction of one electron with one photon, the maximum kinetic energy of photoelectron must be equal to photon energy minus the work function. So the only way to increase the kinetic energy of photoelectrons is to pack more energy into each photon. The only way to increase the energy of photon is to increase the light frequency. Now this photoelectric effect is instantaneous because the electrons do not have to accumulate energy over time. The energy comes pre-packed for the lucky one and takes off immediately. By changing our idea how light gives out energy to the electrons, photoelectric effect is a different ballgame. Under the wave theory, energy is distributed evenly to all the electrons, shaking them and warming them up continuously. Now under the photon theory, energy is delivered between one electron and one photon. The electrons which are lucky enough to be struck by the photons go out of the metal surface. The higher the frequency of light, the larger the energy packet. So Einstein has found an elegant solution to the puzzle of photoelectric effect. Before photoelectric effect, physicists were convinced that light could be fully described by wave. But unfortunately, the photoelectric effect was impossible to understand in terms of classical wave description of light. A particle nature of light is necessary. Davisson and Germer experiment. In 1924, the French physicist Louis de Broglie postulated that all forms of matter display both wave and particle characteristics. According to this hypothesis, electron, just like light, has a dual nature. Two American physicists, C.J. Davisson and L.H. Germer, were the first to experimentally prove the wave nature of material particles in 1927. This is the block diagram of the experimental setup used by Davisson and Germer. It consisted of a nickel chloride crystal, the target, an electron gun G, and a detector. The electron gun produced a beam of electrons. The electron gun used by them consisted of a tungsten filament F and high and low tension batteries. The low tension battery was used to heat the filament. The red hot filament produced an electron beam. A high tension battery was provided to accelerate the electron beam. The detector moved on a graduated circular scale. A sensitive galvanometer was also connected to the detector. Let us find out how they performed the experiment. The electron beam was passed through a pinhole and made to strike the crystal normally. The electrons scattered in all directions, acting like waves. At certain angles, the detector indicated a peak in the intensity of the scattered electron beam. This maximum intensity was due to constructive interference, a phenomenon confined only to waves. Thus, they experimentally proved the wave nature of electrons. Davisson and Germer plotted a graph taking the angle between the incident and scattered direction of the electron beam phi along the y-axis and the intensity of the scattered beam at different values of accelerated potentials along the x-axis. The nature of the graph is as shown. From the experimental curves obtained, the following conclusions were drawn. Intensity of scattering depends upon the angle of scattering phi. A bump or kink always occurs in the curve when phi equals to 50 degrees. This bump or kink increases as the accelerating potential difference is increased. At 54 volt, this bump is maximum and then it decreases on further increase of potential difference. This peak indicated the wave behavior of the electrons. Thus, Davisson and Germer experiment verifies de Broglie's hypothesis of wave nature of matter particles.